more than one basis, but whether other bases exist or not, the standard basis always exists. Other bases also may exist, and any two bases should contain same number of vectors, not same vectors, same number of vectors. So here two vectors are there. So any other basis also should contain two vectors. How to identify a basis? So once you know the dimension, and if cardinality of S is equal to the dimension, and if S is independent, then automatically S is a basis. This is what we discussed. S is a basis. Then one more way of finding this is S is independent, and any two bases should contain same number of vectors. That is called dimension theorem. Every finite dimensional vector space will have a basis. That is called existence theorem. Then we have a theorem called extension theorem. This we have discussed. What is the extension theorem? If any linearly independent set, if S is linearly independent of a finite dimensional and is a subset of a finite dimensional vector space V, then S is either already a basis or S can be extended to form a basis. What is the extension? Adding few more vectors. So yesterday we have seen that extension need not be unique. There can be many extended bases for this. S can be extended. S is either already a basis or S can be extended to form a basis. So what is meant by then in that case? What is the dimension of V? Then dimension of V will be equal to, if S is linearly independent set and cardinality of S is n, then dimension of V is given in one of the papers. Dimension of V will be, if S is a basis, dimension will be equal to n. But if S is not a basis, it can be extended. Extend means we'll add some more. If add some more, it will be more than n. So what will be the dimension? Either it will be n if it is a basis. If it is not a basis, it can be extended. So dimension of V will become greater than n. So what is the relation? Therefore, dimension of V will be greater than or equal to n. Because if it is a basis, because number of vectors in the basis is dimension, dimension of V will be n. Because every independent set need not be basis, may be basis or may be extended. So if it is not a basis, then you can extend. If it is a basis, then dimension of V will be equal to number of vectors in the basis, which is n. But if S is independent, not a basis, then we can extend it. That is adding some more vectors. Then the extended basis will contain already n are there. If add some more, it will be more than n. Then dimension of V will be equal to number of vectors in the extended basis. So in the extended basis, there will be more than n vectors. So greater than n. This is very, very important, given in one of the papers. Today I was collecting the questions, then I found one question based on. So indirectly you are getting, look at this. If V is a finite dimensional vector space over the field of SB linearly independent subset of V containing 10 elements, then dimension of V is. So what is the answer? Direct application. If S is a basis, because S is containing 10 elements, dimension will be 10. But if S is not a basis, it can be extended. Extended means greater. So dimension of V will be equal to greater than or equal to 10. So what is the answer for this? C is the answer.
C answer.
C is the answer.
C is the answer. Like that. Only single correct answer. So this is the direct application. So కొన్నిసార్లు థీరమ్స్ ఇవ్వరు, థీరమ్ స్టేట్మెంట్స్ ఉంటాయి కదా, వాటి నుంచి క్వశ్చన్స్ వస్తాయి. ఇది వన్ ఆఫ్ ద బెస్ట్ అప్లికేషన్ ఆఫ్ ఎక్స్టెన్షన్ థీరమ్. ఇఫ్ ఎస్ ఈస్ లినియర్లీ, నువ్వు మీరు 100 టెక్స్ట్ బుక్స్ ఎత్తుకుతే అది దొరకదు, కాన్సెప్ట్ ఉంటే చేయగలుగుతారు. సో ఎస్ ఈస్ లినియర్లీ ఇండిపెండెంట్, ఎస్ ఈక్వల్ టు ఎన్, దెన్ డైమెన్షన్ ఆఫ్ వి ఈస్. So extension theorem says if it is independent, it is already a basis or it can be extended to form a basis. So what will be the dimension? Either equal to n or greater than n. But we don't know whether S is basis or not. So greater than or equal to n is the boundary. Instead of n, you are given some 50 elements. So greater than or equal to, sorry, 10 elements. So it will be greater than or equal to 10. This is gurtupeట్టుకోండి. One of the applications. Okay. Next, we have another application of this. We have seen dimension formula. Second methodology of finding dimension. Today class is very, very important. How to find dimension. So before going to that, if F is a vector space V is a vector space, F over F is always a vector space. We have discussed earlier also. When do we say V over F is vector space? Shortcut. Long ago we studied. If F is subset of V, automatically it will be a vector space. So you know that F is subset of F. Every field is subset of itself. So F over F is a vector space. So how to find out basis for the vector space? We have to take a vector, we have to get spanning set, independent set. What is meant by spanning? Every vector here should be, every vector here, what is the form of the vector? It will be a scale. F means scalars. So U bar will be of the form some A belonging to F. Every vector we should be able to express as linear combination. Then only we get spanning set. How to get spanning set? Every vector we should be able to express as in the form. What is the form? U bar should be equal to C1 U1 bar, C2 U2 bar, and so on Cn Un bar, where S equal to U1 bar, U2 bar, Un bar. If it is so, if you are able to write, this is what is called as generator. If the generator is independent, then it will become basis. So if more than one vector is there, we will write plus in between combination. Only one vector is there, one scalar, one vector. These scalars should belong to the field F. So if you are able to express every vector of V as combination of some vectors, then these with scalars in F, then these vectors are going to constitute what is called generator for the vector space. So we have taken U bar in V. V is a field. Every elements of fields are denoted by small letters A, B, C, D like that, or A1, A2 and so on. So U bar is equal to A. With this we should be able to express as scalar into vector. Vector means here field only. So we can write this as A into 1, because only one vector, this is there, one vector is there, only you will get C1 U1 bar. More than one vector is there, then C2 U2 bar and so on. A can be written as A into 1. What is 1? Unity of the field. You know that F is a field. Every field has got unity. What is field definition? A commutative ring with unity, and every non-zero element has multiplicative inverse. So it is having unity. So this is in the form, you can write it as A into 1 or 1 into A. This is in the form C into C1 U1 bar. It is in that form. So what is C1 here? 1. Is it there in the field or not? Yes. So we could express this vector, every vector, as 1 into A. So A can be written as 1 into A, that is C1 into U1 bar. So what is C1? 1 belonging to F. Therefore, we say that this is going to be this scalar into vector, or you can also regard, if you want to regard, this can be regarded as A into 1. This is C1, this you can regard it as U1 bar. Any case you can write. So therefore, here we can express every scalar as A into 1. Therefore, we say that this singleton 1 is a generator for V, which is field. And you know that singleton non-zero vector is always linearly independent, which is also linearly independent. This is true for all A. One is fixed. This is true for every vector. Therefore, which is also linearly independent. There being, why it is independent? Single vector, not zero, independent. Therefore, singleton 1 is a basis for F over F. So what is the dimension therefore? Dimension of F over F is, so dimension of vector space V with field F is number of vectors in the basis. How many vectors are there in the basis? Only one vector. So very interesting point is, whenever for any field over itself, dimension is equal to. So you know what are all the fields, you know, you might have done in ring theory. R is a field, complex number set is a field. So Q is a field, rational numbers, many fields are there. And ZP is a field. that is with a suffix prime number, modulo system. So what is the dimension therefore? Very important, direct bits you will get. Dimension of R over R is it 1. What is dimension of C over C? Is 1. Vector space V is R here, F is R. So F over F, C over C 1. And what is the basis for all of them? Singleton 1 is the basis. You should understand what is the basis also, because you may be asked to write what is the dimension of R over R and what is the basis. So dimension is 1, basis is singleton 1. Basis is always a set. Don't write 1. Among options, you may be given basis is 1. Basis is singleton 1. Very important is dimension is 1, but basis is this one. Don't write this. Singleton 1. It should be always expressed in the form of set. You may be given wantedly like this, but always it is expressed in set form. This is tuple. So always write this. This is the right answer. What is the dimension? This is basis. Basis is this. So for R over R also singleton 1. For R C over C also singleton 1, like that. So for Q over Q also, the field dimension is 1. Dimension of ZP over ZP is set of all modulo system we have discussed. Z3 over Z3 1. Prime number, P should be prime. Standard base. Very, very important. So what is the basis? Singleton 1. Dimensions are these. How did we get this? Every element here should be expressible as that the scalar into vector. The common vector for every A that should be fixed. So that vector which is fixed is 1. Therefore, singleton 1 is a basis. Now, what is the dimension of now? Next question is, what is the dimension of C over R? C over C is this. You know that C is subset of C. Therefore, it is a vector space. R is also subset of C. Therefore, this is also a vector space. Then the question is, dimension of C over R, comma, basis for C over R is. Very important. For C over C, 1, C over R. So vector space is C. Every element in this will be in which form? A plus IB, A comma B are real. What is the field here? R. Remember, scalar should belong to field. When you are writing the vector as C1 U1 bar plus C2 U2 bar, a combination, the scalars must be there in F. And these vectors U1, U2, N should be fixed for every U bar belonging to V. Let us see. So you take U bar belonging to V. It will be in which form? U bar will be at the form A plus IB. This you should be able to express it as, scalar into vector with scalars belonging to R. So how will you write this? This can be written as A into 1 plus B into I. Because if I want to write 1 into A, I into 1, I is not there in field. So the scalars must belong to the field. So you have to split carefully. This is in the form C1 U1 bar, C2 U2 bar, where C1 is equal to A, C2 is equal to B, should belong to field. This one. Therefore, every vector for all U bar, you are able to write like this. These are fixed. A, B are scalars. Therefore, which is the basis? Basis for C over R is 1 comma I. These are vectors. It is subset of V. What is V? Complex numbers. So in V, vectors can be complex, but scalar should be real. Okay. So this is the one. This is there. Therefore, dimension of C over R is, how many vectors are there in the basis? 2 vectors. specifically if you want to give a name, cardinality of S, number of vectors in the base is 2 vectors. Okay, so C over R is 1, R over R is 1. Somebody may say, Madam, what is R over C dimension? Can any one of you tell me what is dimension of R over C?
No,
It does
madam.
not exist.
No, ma'am.
It is not a vector space
No,
at
ma'am.
all.
Not a vector
It is
R
not
is
a
not
vector space
subset
at all.
of C.
Because C is not a subset of R. If it is vector space only, we can talk about dimension. Not a vector space, so this concept is not applicable at all. So, very
It is not a
interesting.
vector.
Not a vector space. That will write. Interesting point. R over C is not a vector space. Follow that shortcut. R over C is not a vector space. Therefore, this dimension of R over C concept is not applicable. How about what is the dimension of C over Q? Q is also a field. Q is subset of C. So what is the dimension? Any one of you, can you tell me? Same.
2, ma'am.
Because every this rational number A comma B belongs to, you can write every complex number as, acha, okay, again, A plus IB, where A and B are real. A and B are real. But in this case, A plus IB, they are real. But every real number need not be complex number. So we cannot write like this. Is it not? Because this is real. A and B are real character. A and B are real. If they are real, automatically they are rational or not? No. It can be written as A into 1, B into I. Where A comma B are real is given. But A comma B need not belong to in Q. Why need not be in Q? Because every real number, the real means they may be rational, they may not be rational. They may be rationals or irrationals. According to definition of complex number A plus IB, where A and B are real, but every real number need not be rational. So we cannot say A, B are there in Q. We cannot say. So with this concept, we cannot apply for this. Okay? It is not 2. Don't write 2. So we will discuss later. That is Q over Q, 1. Okay. Next, we have a concept now, how to find dimension using third method. The third method for this is dimension is equal to standard formula. Dimension of V is equal to number of free variables. If it is given with condition, dimension of W is equal to number of free variables, whether it is W or V, anything. Number of free variables. Number of free variables. This is another methodology of finding dimension. Number of free variables in W. How will you do this? For example, what is the application? If W is equal to set of all B plus C, C, B. BC belongs to R. That's scalars. Then dimension of W is basis for W is this is another method. So that means if you are given W, every subspace is a vector space. This is a subset of which space? Any one of you, can you tell me? This is subset of which space? How many components are there?
R3, ma'am.
R3.
R3.
Plus 3 components are there. So It is subset of R3. It is a subspace of R3. We have done questions of subspace. So whenever it is without some conditions, automatically it will be a subspace. Already we have discussed long ago. What is the dimension now? So dimension of W is number of vectors in the basis. One formula. Another formula is, suppose you are asked to find only dimension, then waste of time finding basis. Instead, directly you can get the dimension using the formula number of free variables. How many free variables are there here? B and C are real. That means free. You can give any value for B and C. Number of free variables are 2. So dimension is 2. So dimension means number of vectors in the basis. Then what is the basis? That also we can find. How to get the basis? Every vector in this, you should be able to write it as a combination. How do we write this as combination? B plus C, 0B plus C, B plus 0C. You can split this. B, 0B, B plus C, C, 0C. This can be rewritten as 1, 0, 1. 1, 1, 0. So you are able to write this in the form C1 U1 bar, C2 U2 bar. So this is what is the generator therefore? 1, 0, 1, 1, 1, 0. This is a generator. How many vectors are there in generator? Is a generator for not for R3, for W. Dimension of R3 we already know it is 3. This is subset of R3. Now dimension of W is 2 and cardinality of S is also 2. S contains 2 vectors. Therefore S is basis. By yesterday's shortcut extension theorem. Whenever generator contains number of vector dimension coincides with the dimension, then it will be automatically a basis. If it is independent also it is a basis. If it is a generator also it is a basis. Yesterday we have discussed. So therefore S is automatically a basis. What is the dimension? 2. This is the basis and the dimension is 2. So for finding dimension you need not do all this. Directly number of free variables will give you the required dimension. So for W, what is the basis now? We got it as 1, 0, 1 and 1, 1, 0. That's it. Okay. Next. Is it clear for all of you? I'll give you one question. You tell me what is the dimension. If W is equal to set of all vectors of the form S, 2S, 3S. S is free variable or S is scalar? S is scalar or free variable. So then dimension of W is
1.
obviously what is the dimension?
1, ma'am.
1. Only one
One.
free variable. What is the basis? What is the
1,
basis?
2, 3.
1, 2, 3.
1, 2, 3. 1, 2, 3, ma'am.
Just 1, 2, 3.
1, 2,
Singleton 1, 2, 3. Always you should write in set form. Among options you will be given 1, 2, 3 like this. This is basis or this is basis. Always you should write in flower bracket. Don't write. This is vector, not a set. Basis should be set. Therefore you will get it. Okay. So be careful. So this is the one. Now another question. Suppose you are given. Another question is, suppose you are given W is equal to set of all A plus B plus D, B 2C D. Then where A, B, C, D are free. So what is the dimension? Free or scalar? So dimension is 4. C is not there in all. Every variable A is not there in all. Overall, how many free? Not required that every free variable should be present in every component. Need not be. Overall, are they present or not? That is important. So then dimension of W is 4. So without doing finding the basis, you are able to say what is dimension. Basis also you can try for this question. Express everything as A, B, C, D. A plus B plus 0 C plus D. 0 A plus B plus 0 C plus 0 D. 0 A plus 0 B plus 2 C plus 0 D. So here 0 A plus 0 B plus 0 C plus D. Split like I did earlier, you will get basis. Okay, that you can try as homework. Now, for set of all polynomials, you know that set of all polynomials Pn is going to be a vector space. What is Pn? Polynomials of degree at the most n. So, a0, a1x, a2x square, an x power n. Maximum degree n. What are a0, a1, a2, an? They are nothing but scalars. So, what is the dimension of Pn then?
N plus 1.
N+1, ma'am.
Among options, n will be given. First option will
N.
be n. Second option will be n plus 1. So, why it is n is a0. Every vector can be written as how many free variables here? Same model. a0, a1 to an. 1 to n, n element, n scalars. One more is there, so n plus 1. Number
N
of free
plus 1.
variables, n plus 1. What is the basis? Standard basis. Very important. Standard basis is
1x square x. It's on x power n.
1x
one
square.
x square x power n. This is the standard basis. a0 into 1 plus a1 into x, a2 into x square, an into x power n. So what are the vectors? 1x square x power n. This is the standard basis. Okay. Now what is dimension of P3? P3 is, don't write 3.
4, ma'am.
Dimension of R3 is
3.
3. This is where the confusion is. For R3, suffix that is standard basis contains 3 vectors. Therefore, 3. But whereas dimension of P3 means polynomials of degree at the most 3. If it is Pn, n plus 1, so 3 plus 1, 4. So without confusion, you should be able to. What is the standard basis for this? 1 x square x cube. You should write up to x cube because P3 is there, maximum degree 3. That is the reason why number of vectors in the standard basis 4, so you are getting 4. For R3, what is the standard basis is 1 0 0 0 1 0 0 0. That is the reason why its dimension is 3. Number of vectors are 3 in the basis. Fine, no? So this is how we find out for this. Next model for this is, suppose you are given with condition. That is, question is, then I forgot to ask you one more question. Dimension of Mn, matrices of degree n over the field F. N means n by n matrices. It's n square. N into n. N means n by n. N square. Standard basis. Mn, dimension of Mn over F is n square. Okay, over the field. Now, for example, why it is so? Dimension of M2, for example.
4.
2 into 2, 4. 4 means, what is the standard basis then? M2 means 2 by 2 matrices. What is M2 means?
1 0
Set
0
of
1.
all matrices, 2 by 2 matrices, such that A, B, C, D are real. If it is complex, A, B, C, D are complex. Whatever is the field, it belongs to the field. So we can write it as A, B, C, D can be written as A into 1 0 0 0, B into 0 1 0 0, C into 0 0 1 0, D into 0 0 0 1. Therefore, what is the standard basis? S is equal to 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. Is standard basis. Standard basis. Not only for Mn, for M2 over R, M2 over F in general. R also same, C also same. In general, for M2 over F. If it is C, ABCD will be complex. Same story. The scalar should belong to corresponding set. So, how many vectors? 4. 2 by 2 means 4. Because 2 by 2 means matrices will contain 4 elements. So, you will have 4 matrices. Number of free variables will be 4. That method also you can apply. M2 over F. Set of all ABCD such that ABCD are belonging to F. How many free variables? 4 free variables.
Four.
So, what will be the dimension? 4. Number of free variables. That method also you can apply. Number of free variables, which is equal to 4, because 4 scalars are there. If it is Mn, n scalars will be there. Therefore, n into n, n square. Understood now? So, n square scalars will be there. So, dimension will be equal to n square. So, in general, what is the dimension of Mn over F? N by n, that is n square. M2 over F, same. M2 over C, same 4 is the answer. In general, M2 over Mn over F is n square. Remember that. Next one, another model for this. If you are given polynomials, we have seen matrices. So, if W is equal to set of all ABCD such that A plus B minus 2C plus D is 0, then dimension of W is
3, ma'am.
3, madam.
3. Why
3.
3 is? One condition is given to you. So, in this condition, ABCD, if you take ABCD, condition is given. So, you can write either A in terms of BCD or B in terms of ACD or C in terms of ABD or D in terms of ABC. You can take any one of them. If you take A equal to, if I use the condition, A is equal to, if I take it, sorry, A plus, A can be written as minus B plus 2C plus minus D. I am taking BCD as free variables. Okay. Somebody may say, why are you taking like this, madam? Take B. What is speciality about this? We can take. Okay, you can. ACD are free. In any case, whether you take like this or like this, free variables are different. But how many free variables? Only 3. So here BCD are free, here ACD are free. How many in number? 3 in number. Maybe free variables are different, but how many means 3. Count is the same. So I can express A as minus B plus 2C minus D. So B means B, C means C, D means D. Which are free then? BCD are free.
BCD.
Are free. So what is the dimension? Number of free variables. So dimension of W is equal to, in appearance 4, but after using condition, they got reduced. So when it is without condition, answer is 4. With condition, answer is 3. So for such questions, when conditions are given, then we have 2 models. One model is, look at the conditions. The conditions, are they independent? That means no variable in common. So here only one condition is given. So happily, that is only independent. So we have another formula for finding dimension. This is method 4. So what is the method is, dimension of W is equal to, if condition is given, number total variables n, that is total number of variables, minus number of independent restrictions. Independent restrictions. Number of independent restrictions. So here in the previous question, n means total number of variables. How many variables are there? 4. N denotes number of variables, number of scalars, variables or scalars, minus number. So here how many variables are there? 4. So n is 4. How many conditions are given? 1 condition. So 4 minus 1 is 3. This is very, very helpful. So how many conditions are given? Only 1 condition. How many variables? 4. 4 minus 1, 3 directly. Instead of doing all this, directly you can get the dimension. So let us see again. One more. Somebody may get a question. Madam, suppose 2 conditions are given, then how do we do that? Yes. So question. If W is equal to set of all A, B, C, D such that B plus 2C is equal to 0, A plus D is equal to 0. 2 conditions given. They are independent. No variable in common. Here BC, here AD. They are called independent restrictions. These are called restrictions. They are called independent restrictions. Independent restrictions means no variable in common. Then what is the dimension of W? So dimension of W is dash. So total variables are 2, n equal to 4. Number of restrictions, independent restrictions. Number of independent. Independent means no variable common. Restriction. 2. Therefore, 4 minus 2 is 2. Even otherwise, if you don't know this formula, then how to do it? You can write B as minus 2C as before. A is equal to minus D. Substitute here. Then ABCD is equal to W is equal to set of all ABCD. A can be written as minus D, B can be written as minus 2C, CD. How many free variables? 2 free variables. C and D are free. So what is the dimension? Number of free variables. So dimension of W is equal to number of free variables is equal to 2. Even if you apply this method also, you are going to get same answer. So this is another method. So one method is total variables minus number of independent restrictions. Or second method is solve it. Write in terms of free variables. Then also you'll get the same. Now this story, this formula is only when the restrictions are independent. That is no variable common. If some variable is common, we cannot apply this method. Then how to do it? That's going to be the next model. So if Q is equal to W is equal to set of all A, B, C, D such that B plus 2C plus D is equal to 0, A plus B plus 2D is equal to 0. Let us see. Then restrictions are not independent because there is one variable common. More than one variable common. B is common, D is common. So we cannot apply 4 minus 2 is equal to 2. We cannot apply. Then how to do it? Then dimension of WA. In that case, we cannot do. So which are free, that we have to understand. So number of free